Take a look at this target molecule. Why don't you try your hand at synthesizing it and then compare what you did to what we do here. Remember step 1, consider the functional groups that you need to make. Hey, there aren't any. This is an alkane, and because it's an alkane and we need to make it, that probably means that we're going to be making carbon-hydrogen bonds, do a reduction at the end to make the alkane itself. In step 2, we need to count the number of carbons in the target molecule. Well, this has 9 carbons. It's a C9 molecule. And then step 3, we'll consider the molecules that we have available as starting materials and figure out how many carbon-carbon bonds we need to make, if any. Well, you see here that we can have at most 4 carbons, and we have a C9 molecule. So that means we need at least 3 different pieces to put together, because 4 plus 4 would be 8, so we can't make this by just 2 pieces. We need 3. What ways do we know to make carbon-carbon bonds? Well, at this point, you really only know one way that's versatile at all for making carbon-carbon bonds, and that is alkylation of an alkyne. So, take a look. This target molecule could come from this alkyne. Well, it could come from a lot of other alkynes too, so why did I pick this one? For this molecule, here's a carbon-carbon bond we need to make, and here's a carbon-carbon bond we need to make. So I have picked an alkyne that lets us make 2 carbon-carbon bonds. And remember that the halides we use need to be primary. Well, this is a primary carbon that we'll be using, and this is a primary carbon that we'll be using. So we could use 2 primary alkyl halides and acetylene to put together the carbon-carbon bonds we need to make this carbon skeleton. And then the last step of our synthesis will be reduction of the alkyne to make the alkane. So what we're saying here is this alkyne could come from 2 different pairs of compounds. On the top we have an acetylene plus an alkyl bromide that's primary. And on the bottom we have a primary alkyl bromide plus an acetylene. So either pair looks like it would work well. Both the alkyl bromides are primary, as we pointed out. So here we go. There are 2 alternative routes. Let's look at the top one first. If we follow that top route, what we need to do is make that acetylene from an alkyl bromide plus acetylene itself. And of course we would need to make this alkyl bromide, which would come from propylene. We know that we can add HBr to an alkene in an anti-Markovnikov sense to make primary halides. If we followed the lower path, we would need to make the isobutyl bromide from isobutylene. We know that can be done. And we would need to make this alkyne from acetylene plus N-propyl bromide. We know that can be done. And we've already indicated how N-propyl bromide would be made up here. So we don't have to plan that synthesis again. And we don't have to plan the synthesis of this isobutyl bromide here because we've written it down here for the other case. So what remains to be done then is plan the synthesis from front to back. If we start with acetylene, we can treat this with sodium amide and isobutyl bromide to make the substituted acetylene. Repeat the alkylation procedure to make the disubstituted acetylene. And finally, reduction using hydrogen and a metal catalyst will make the alkane. But wait, we haven't said yet how we'll make the alkyl bromides we need. Those alkyl bromides will be made using anti-Markovnikov addition of HBr. And those conditions are HBr plus a dialkyl peroxide. One of them will start with isobutylene to make isobutyl bromide, and the other one will start with propylene to make N-propyl bromide. And there you have it. First we did our planning by identifying what carbon-carbon bonds we needed to make. We knew that we'd use an acetylene to make them. We knew that we had to pick primary alkyl bromides as the alkylation partner. And from there we just worked backwards until we got to the C4 hydrocarbon pool that we had available for starting.